All right, so here in 1.3 part 2, you took a minute, hopefully from memory, to fill out question 1 and question 2. Again, if you had trouble filling these in, you can definitely look back a page or two in your notes. 1.3 part 1 has those filled in for you. And yeah, we're going to go ahead and talk about these things we call identities now. So an identity, quite frankly, is just things that are equal to each other. So when you are exploring a possible identity for A plus B, perhaps you foiled that. And if you foiled that, you probably came up with A squared plus 2AB plus B squared. So these two things are equal to each other. This can be logically replaced with this. So it's the idea of subbing formulas into each other, or for each other, I should say, that's going to be huge for this section. So recognizing one equation as equivalent to another is huge. A squared minus B squared, maybe you factored that in your Algebra 3 class, or your Algebra 2 class. That's called a difference of two perfect squares. So you square root A squared, that's A. You square root B squared, that's B. And then because we need this to be a minus sign in here, and we need our outers and inners to cancel, you probably have a plus and a minus hanging out in your parentheses. Remember, another variation on this would just be to use your commutative property of multiplication and reverse the order. So this would also be the same as A minus B, A plus B. So I have three identities, three identical formulas in there. So these three items are logically equivalent to each other. I'm going to go ahead and wager that for part C, a lot of you are using your distributive property to produce an identity. So you were taking A times B and adding that to A times C. And then you could rearrange this even. This could be AC plus AB. Or this could be CA plus BA. Lots of different answers. It's having that flexibility in your algebraic thinking that's going to be huge for this section. If you don't understand what I'm writing, by the way, feel free to flag me down and be like, wait, what property did you use there? All right. Couple more from your warm-up. Do you remember negative exponent rule, kind of the bad puppy rule? What do you got there, Bree?
Don't you flip it and make the bottom, I don't know, do you just flip it?
Yeah, just the reciprocal. Yeah, it's just 1 over A. It's not really the reciprocal. That was a poor word choice on my part. I'm so sorry. Yeah, if you have a negative exponent, to make that a positive exponent, you just move it to the bottom. So A to the negative first is actually 1 over, whoops, grabbed the wrong tool there. That's 1 over A to the first. And then I kind of talked about A plus B already. There's really only, I think, one rule I could apply to this is just that commutative property. So A plus B is just B plus A. And I actually think, that was probably the easiest of all of them. All right. So what you produced in this warm-up, these are identities. And now we just have to throw sine and cosine into them. That's what we're going to do. So where you see A, that might be sine. Where you see B, that might be cosine. Where you see C, that might be a tangent. So we're going to write formulas today. All right. A couple things. I'm going to go ahead and introduce your new identities to fill in. So here in key point 1, you have some blanks to fill in. Along with your co-function identity, there's basically 3 sets of identities that you have to dedicate to memory. So these will be the things that are, on upcoming quizzes and tests. You have your reciprocal identities, which we kind of took care of. You have your quotient identities. And then you have your Pythagorean identities. So there's 3 types of identities on your quiz tomorrow. You have your reciprocal identities, you have your quotient identities, and you have your Pythagorean identities. Okay, reciprocal identities. I'm going to take this line by line for you. It's a lot of information. Let me cover some of this up so you're not too overwhelmed. All right, that first line there. Remember we defined sine as the y-coordinate? This was your opposite over your hypotenuse on the right triangle. But if we're on the unit circle, this hypotenuse, this radius is always 1. So it always ended up just being your y-coordinate. But what I need to start to transition you to is off the unit circle. So instead of doing opposite over hypotenuse, we're going to do y over r, our y-coordinate over our radius. You might recall that to find sine, you could flip cosecant. So the formula you jot down is just 1 over cosecant. And then for cosecant, you just flip your values of sine. So if you're like struggling to memorize things, I'll just go ahead and let you know that if this chart is the thing that you're going to need to fill out, like in your homework tonight, you could just work your way across. So if we're looking at cosecant and we understand that it's the reciprocal of sine, you're just flipping this. So the reciprocal of y over r is r over y, or 1 over your sine value. All right, cosine, pretty similar. In this case, it's your x-coordinate, right? So you're doing x over r, or 1 over your secant. So you could flip your secant to find cosine. That's what that means. Secant is just your r divided by x, or your 1 divided by x if we're on the circle. So this becomes 1 over your cosine value. Okay. Last but not least of your reciprocal identities is tangent. Remember, tangent is just y over x, your y-coordinate divided by your x-coordinate. And so we can extend that definition to be 1 over cotangent. And then the cotangent of theta is just x over y. That's 1 over your tangent. All right, that's line number 1 done. Those are your reciprocal identities. Quotient identities, there's only 2. So your quotient identities, remember that if tangent is y divided by x, and y is sine, and x is cosine, another way of writing tangent is just to understand it as sine over cosine. So if sine is y and cosine is x, you could write tangent as sine over cosine. The other quotient identity is for cotangent, and I just flipped what was right next to it. So it's kind of like a nested reciprocal identity also. Remember, if x is cosine and y is sine, a quotient identity for cotangent would just be cosine over sine. And it's called a quotient identity because we have quotients between sine and cosine. You're dividing sine by cosine. So lastly, we have our Pythagorean identities. Woo, almost deleted the whole thing. Hold on. Get this box out of the way here. Okay, so to start, let's just focus on that one. It is the Pythagorean theorem in disguise. sine squared theta plus cosine squared theta equals 1. You have the Pythagorean theorem. That's why it's called the Pythagorean identity. Remember, Pythagorean theorem goes a squared plus b squared equals c squared. This is your x squared plus y squared equals r squared. If you're thinking about a circle, or if you're thinking about a right triangle nestled in your unit circle, you got your x squared plus your y squared is your 1 squared. So that is just the Pythagorean theorem. Again, I'll show you how that works. Okay, and then the next two, I call this one like the grand poobah. It's like the most important Pythagorean identity. The next two just come from this one. So the next two are like, it's like little grandchildren, or like nieces and nephews, however you want to refer to it. But let's talk about those. So the next one, and you'll see how they're kind of tied together here, if I can get rid of this box. You have 1 plus cotangent squared theta equals cosecant squared theta. 1 plus cotangent squared theta equals cosecant squared theta. And then 1 plus tan squared theta equals secant squared theta. I'm not the biggest fan of memorizing facts. When I was in trig as a kid, I couldn't remember those. I couldn't. I had to actually think about where they came from, and then I was like, oh, that makes sense. So that's what I'm going to show you. Because I think if you can understand like why they're there, then they stick a little better. So the rest of the lesson today is just talking about the Pythagorean identities and like why they exist. What are they here for? Like why are these here? So that's what we're going to do. It's a little bit of proofs, which I promised you. Is just to explain where these Pythagorean identities come from. So let's do it. All right, in example 1, I'm just showing you how this guy here actually comes from the Pythagorean theorem. How does that come from our friend, the Pythagorean theorem? So let's start with the Pythagorean theorem. This goes a squared plus b squared equals c squared. And I'm going to draw that as a right triangle. If I'm labeling that as a right triangle, your c value is always your hypotenuse. And then a and b are legs. Everybody cool with that? So far, a squared plus b squared equals c squared. Pythagoras took care of that for us. It is something that works for all right triangles. The sum of the squares of the legs is equal to the square of the length of the hypotenuse. All right, but remember back in the day, you know, we're putting these triangles on this thing we call the coordinate plane. And furthermore, we're making this thing a triangle that's in a circle. And this is the part I'm always real bad at drawing. Probably should have swung that out a little bit more. But that point on the circle, you can call it P if you want, is now the point A, comma, B. If you need to extend your axis out a little bit, make you feel better, go for it. And since this thing is actually technically our unit circle, that C value is a radius, and the radius is 1. Bless you. So now back to my Pythagorean theorem. Remember, you can divide anything by 1, and you don't actually change its value. Like division by 1, like if I take a squared and divide it by 1, it's just a squared. So I just divided everything in the problem by 1. But that has a very special meaning because 1 is actually the value of the radius on our unit circle. So if I rewrite this a squared over 1, using my quotient property of exponents, you know, you got a over 1 squared plus b over 1. Oops, that's supposed to be red. Grabbed the wrong tool, sorry. So we got b over 1 squared equals c over 1 squared. I'm like color challenge today. Bouncing back to our circle, if you look, so I have a squared plus b squared equals c squared. Very much, I just kind of doctored it up with what I know about identities and the, you know, multiplicative identity, quotient properties. So what I actually have, if I take a over 1 and I put it on the circle, a is my adjacent side. So if that helps you, you could write that down. A is our adjacent side to an angle theta. B is what we would call our opposite side. So when I look at a over 1, this also gets replaced. A over 1 is adjacent over our hypotenuse. If you look at the triangle, squared. B over 1, if you look at the circle there, B is actually the opposite side to theta. So B in my head is now taking the place of opposite, and 1 is your hypotenuse. I guess I should make my hypotenuse black, huh? Because it was 1. And don't forget your squared. So that's that. And then I could do C over 1. But C in this case was actually special, right? C had a value. C was 1. So what I have on that other side of the equal sign now is 1 over 1 squared. Because C on our circle was 1. All right, last little bit. We are almost done. Adjacent over hypotenuse, my friends, that is cosine squared. Opposite over hypotenuse, that is sine squared. And then 1 over 1 squared, that's just 1. And you're like, wait, Mrs. Lucas, the identity said sine squared theta plus cosine squared theta equals 1. You're right. That's our commutative property of addition. So I can just reverse those if that part bothers you. And I'm pretty happy because I started with the Pythagorean theorem and I arrived at our grand poobah identity, the most important Pythagorean identity of the 3. It's sine squared theta plus cosine squared theta equals 1. This proof was for your notes and for your visual entertainment. Will you see a problem like that on a test? No. But I think it helps a lot of kids to see where the heck that formula comes from. And so that's why that's there. I had to understand it in order for it to go in. So hopefully this helps with that. So it's just the Pythagorean theorem in disguise. All right, we are almost done. Almost. We're going to go ahead and pick up with example 2 here. Because now I can take that grand poobah identity and turn it into the other 2. So what we're going to try to tie together is how sine squared theta plus cosine squared theta equals 1 can be turned into this right here. So the mission here in example 2 is just to use sine squared theta plus cosine squared theta equals 1 to show you that 1 plus tan squared theta does indeed equal secant squared theta. So this is kind of where we left off. We are supposed to start with this. So I'm going to show you how I called it yesterday the grand poobah of Pythagorean identities, I'm going to show you how this one gives you the other two. And then we're going to see what you know. So we start with what we're given, that sine squared theta plus cosine squared theta equals 1. And whenever I do these sort of proofs, I always, begin with the end in mind. So what I observe on the right side here, where 1 is supposed to be, is the idea that that 1 needs to somehow turn into secant squared theta. So I'm going to rewrite secant squared theta, recalling what I know about secant. You might recall, and you could draw your little thinking cloud there in your notes, you might recall that secant, courtesy of our reciprocal identity, is actually, you ready for it? Here it comes. 1 over cosine. I know, right? Brain exploded. So you can go ahead and jot that down in your notes. That's where we're at right now. What I'm doing is I'm going to replace this whole idea of 1 by dividing it by not just cosine theta, but cosine squared theta. And I have to do squared because this was secant squared. So it's actually 1 over cosine squared that gives you the secant squared. Everybody cool with that? See how I turned that right side into 1 over cosine squared? Okay, here's the fun fact though. What you do to one side of an equal sign, you do actually have to do to the other. So I'm just going to go ahead and divide everything in the problem by cosine squared. And then, oh, look at that. Oh my goodness, it's so pretty. Okay, so see this right here? Cosine squared over cosine squared. Algebra 3 fans, that makes 1. Bring down my plus. All right, I have a question for you, my very smart period 4 trigonometry students. Anybody remember what sine over cosine was from yesterday? Hopefully you do, Parker. Yes. It is tangent. Woo. Sorry. So this guy here, sine squared theta over cosine squared theta, according to Parker, that is going to be tan squared theta, which is what I needed. Do you see that? 1 plus tan squared theta. Oh, I got tan squared theta plus 1. We're going to do one more step. And then what we understand is that 1 over cosine squared theta is this right here. Replace that. That is secant squared theta. Now you could use your commutative property there. So this would be 1 plus tan squared theta on the left. Not that you have to do that, but it is equal to secant squared theta. So I was able to turn sine squared theta plus cosine squared theta equals 1 into my other Pythagorean identity because I was able to divide everything by cosine squared. Yes?
So, like, what's the point?
The point is just to show you how that's a great question. I love that, by the way. How that first identity at the top, if I just mess with it algebraically, I get this one. You won't have to do this. I'm just showing, it helps kids if I show them where it comes from. So hopefully this helps you, memorize your identities a little bit. That's the goal. I'm gonna do it one more time. I wanted to show you where 1 plus cotan squared theta equals cosecant squared theta. So we're gonna do that. So just scrolling down a little bit. Again, beginning with the end in mind, what I observe is that cosecant squared theta can be rewritten a bit. Does anybody know what cosecant squared theta is equal to? As a reciprocal identity? Its reciprocal identity? So think back to your chart. You could even look back a little bit, you know, for now.
Is it sine?
It's not equal to sine, it's equal to 1 over sine. Yeah, so close. But you were kind of right. I think that's what you meant, actually. So yeah, cosecant squared theta is 1 over sine squared theta. And again, the goal, Parker's like, what is the point of this? I love that question. Cut straight to it, is to show you that I can take sine squared theta plus cosine squared theta equals 1, and I can transform that back into this other identity, 1 plus cotan squared theta equals cosecant squared theta. So that's what I'm going to do. I'm going to actually just divide, you know, in the previous example, I divided everything by cosine squared theta. But in this case, I'm going to need to, you know, this was like a thought bubble last time. I'm going to need to divide everything by sine squared theta, because that's how I can get cosecant squared on the other side. So what you do to one side of an equal sign, you have to do to the other. Good job. So sine squared theta over sine squared theta. Oh my goodness, I love it. I love when stuff cancels. So there's my 1. Bring down my plus. Anybody remember what cosine over sine is equal to? Sine over cosine is tangent. What do you think, Ashley? Oh my gosh, so good, yes. But don't forget it's squared this time around. So good, Ashley, thank you. And then 1 over sine squared theta, that's just our cosecant squared theta. So that's it, done. So that was me just showing you how you could turn sine squared theta plus cosine squared theta equals 1 into 1 plus cotan squared theta equals cosecant squared theta. So they are just sort of arrangements of each other.